So 2.1. I'm not going to go through everything he did. I'm just going to basically summarize it. He gave you the limit definition of a derivative, right? So a derivative. What does a derivative tell you? What piece of information does it give you? Sorry? Well, it tells you something about the function or the graph.
How the function changes with respect to the x-axis.
Yeah, that's right. Okay, so if I wrote how the function changes with respect to the x-axis, you're writing this. Correct? Change in y over change in x, which I could write this way. Anybody recognize that formula? What is that formula? That's the slope formula. Okay? The derivative is the slope of the tangent line. Did he say that?
I think so.
I think so, vaguely. Slope of tangent line. And he gave you the limit definition of it, right? So delta x goes to 0, f of x plus delta x. That is the limit definition of the derivative. What were the symbols for the derivative? He gave you 3, I think, or 2 at least.
dy over dx.
So dy over dx is one of them. Or f prime. And then if you write it as y equals, you can write y prime as well. Did he show you anything else? Okay, those are the 3 main ones that you will see. Okay, depending on what you're doing, you'll use one or the other. The dy dx, nobody likes that, but it actually makes more sense when you're looking at certain types of questions, what we'll get to later on. But these just mean the derivative. That's all it means. Okay. Nobody uses the formula limit of f of x plus delta x minus f of x over delta x. Because as you saw, he gave you a few questions, I think, to do. It's very cumbersome. You're solving limits, which takes a long time. So there are sort of, what's the word? Fast ways, quick ways to do them. Okay, and that's what 2.2 is all about. But before we move on to that, I want to talk about, because I know we didn't talk about this, is when do derivatives not exist? So really what that's saying is, when does the limit not exist? Right? Because a limit, or the derivative is a limit. So if I say, when do derivatives not exist, I'm saying, when does this limit not exist? So don't think of, just think of a graph and tell me when limits don't exist. What's one example of when a limit does not exist on a graph? It's not continuous, so there's a hole at that point. Okay, that's not always the case, but is in this one. So I'm going to call it an undefined point. So like that. You cannot do a derivative at this point because the point doesn't even exist, right? If I said the derivative is the slope of the tangent line, and you're trying to draw a tangent line there, there's nothing to draw a tangent line on, okay? So when there's a hole at that point. Everywhere else, there's a derivative all along here, but at that point, it doesn't work. What would be another one?
If you're limit like jumps.
That's okay. So that would be okay. That you're right. That'd be the same type of thing. So I could say this is still an undefined point. So like that. You can't do derivative at C for that one either. Vertical asymptotes. Because the limit of that is infinity or negative infinity, right? So we'd say the limit doesn't exist. So, and you can't, there's no point there. It's an undefined point as well. Can't draw a tangent line at that point. Okay, there's two other ones.
When the limits, like, when the limit from the left gets squared to the right.
That would be this one right here. But you're right. Like, but that would be that one there. What about this? I'll draw the graph. Anybody here done chemistry 12? What does that graph look like? It's like a buffer graph, right? What's the slope at that point C? Well, it's over 0, but it's vertical, right?
Yeah, it's like straight up.
So it's straight up and down. So that's a vertical slope that's straight up and down. So what's the slope of something that is straight up and down?
0.
It's infinity, right? Yeah. So vertical tangent line is what we're going to call that. So vertical tangent line, and then the fourth kind makes sense once you know a little more about the definition of a limit, but I'm just going to give you a hand-waving explanation of it. Or, whoops. Sharp turns. So the most common type of sharp turn would be an absolute value graph. Okay. So it's where the graph is going in one direction and then it just suddenly switches. There's no sort of curvature or anything like that. It's a fast switch. And you can think of it, this is a very hand-wavy explanation, but once you know more about limits, then you can look at why this is. If I try to draw what's a tangent line? I know we told you that.
Line that hits 1 point.
Hits the graph at 1 point, right? So if I have a sharp point here, I can draw a tangent line like that, right? I'd only hit it at 1 point. I can draw it like that. I'd only hit it at 1 point. I can draw it like this and only hit it at 1 point. Or like this. Basically, there's an infinite number of ways you draw a tangent line, but you can't. So to say, you can't really draw a tangent line at that point. Okay? So derivatives do not exist at sharp turns. Now that's very hand-wavy. All right? There is a formal way to determine that, but you need to know a little bit more about derivatives. So we're not going to worry about that right now. So just know sharp turns. And another type of sharp turn is called a cusp. And cusps look like this. That would be a cusp. This is a sharp turn. It's probably easier to see this one. It's a sharp turn. And cusps occur usually when you have fractional exponents. So something like x to the 2/3. And again, once we know a little bit more about derivatives, you'll see why the derivative of this function does not exist at that point C, or in this case, 0, but something like that, okay? All right, so four ways that derivatives do not exist. One, undefined point. If the point doesn't exist, you can't draw a tangent line. If you have a vertical asymptote, that kind of ties into this, kind of the same thing. If you have a vertical tangent line, because that means the slope is infinity. and if you have a sharp turn. Okay, that's when derivatives don't exist. All right. Any questions about that? Is that okay? All right. Now, I just want to talk. This is going to finish off 2.1. So, continuity. You've talked about continuous functions and whatnot. If a function has a derivative at a point, then it is continuous at that point. Okay, which makes sense because when do you not have derivatives? When it's not continuous, right? So if a function is, if a function is, so the fancy word is differentiable. Oops. At x equals c, then f of x is continuous at x equals c. But the reverse is not true. All right. So if you can take the derivative of a function at a certain point, it has to be a continuous function at that point. It can't have a gap, right? By just looking at these things up here. But just because it's continuous does not mean it has a derivative. And you can see that with this one. This is a continuous function, right? But it's not differentiable at that point, or in this case, this point. Okay? All right, that's the sort of mathy stuff. Now let's do the more practical stuff that everybody uses. Are there any questions about those? Know the 4 ways that derivatives don't exist. That's important. That's really important. Okay. Going once, going twice. Yeah.
Should I actually explain what you mean by if a function is differentiable? Again?
If you can take the derivative. The derivative exists. I'll say that. This means, you know what? I'll just say f prime. F prime of x exists. You can find the derivative. That's what that means. Anything else? Okay. 2.2. Derivative rules. Or differentiation rules, or whatever you want to call them. All right. This is the stuff that's going to make up the majority of your quiz next week and or your test in the weeks to come. All right. So, all right, we'll just start with the basic one. The constant rule. So if I say, okay, y is equal to c. C is some constant, okay? Now we can just do this visually at first. What does the graph of y is equal to c look like? I.e., if I said c was 4, what does the graph of y is equal to 4 look like? It's a flat line, right? At c. Okay. What's the slope of that line? Right? This is a line with slope 0. When I write m, does everybody know I mean slope? That's what I mean, okay? The slope is 0. Therefore, if the flat line has a slope of 0, all right, and I say y is equal to c, What does y prime equal? 0. It has to equal 0, right? Because by definition, y prime is the derivative, and the derivative is the slope of a tangent line. And what's the slope of that line? 0. Therefore, y primed of c has to equal 0. Does that make sense? The derivative of any constant is 0. So we can write that as this. We can say dx, this is how you write it, of c. So this reads as the derivative of c. This means with respect to x. You'll see later on, this will become important, okay? All right, equals 0. That is your first rule. Doesn't matter what the constant is. So if I said, I don't know, if I said y is equal to 10, and said, what's y prime? You would say? 0. Done. Easy. Okay? All right. The power rule. I'm not doing a proof of this. I'm just going to give it to you. I think that you can look up the proof of it if you want. I think if you go to the website of the book, it's got all the appendices. It has the proofs of things. So the power rule says this. I'll write it out and then we'll talk about it. Sorry?
It's kind of like logs.
Kinda, but there are no logs in it. There's special derivative rules for logs, which is later on in the course. This is just for polynomials. So x to the n, this is for polynomial function. Actually, that's not true. Any function has an exponent that is not x. Okay, it says the derivative of x to the n with respect to x is nx to the n minus 1. All you do is take the exponent, drop it down in front, that's where this n comes from, and take 1 away from the exponent that was already there. And that gives you the derivative. You don't have to do that limit definition. You don't have to do this. That takes forever. Where'd it go? You don't have to do this thing. Right? Because even for something like x squared, which is pretty straightforward, I think he had you guys do that. It takes up a lot of space, right? You can do that in one step now. So let's do some practice examples. So if I say f of x is equal to x cubed, and I say, what is f prime of x? Take the exponent, drop it down. Take 1 away from 3 to get? That's it. That's the derivative. Okay? All right, cube root of x. What's the problem here? That's not a problem. We just don't have an exponent yet, right? We have it as a cube root. We want exponents. When you're doing derivatives, you want exponents, because if you have exponents, you can use this rule. Okay? So how do I write this with an exponent? So that means x to the power of 1/3. Therefore, when I say what is f prime of x, drop the 1/3 down. Take away 1 from a third. I'll write it out. You'll get good at just doing this in your head. So you're going to get 1/3 minus 3 over 3, which is negative 2/3. So you can write it like that. Or you could write it like 3x to the 2 over 3. Or you can write it as 3 cube root of x all squared or whatever. It doesn't matter. Okay? But now you can see why. Remember I told you in this one. Sorry, I'll put this back up in a sec. I said you had undefined derivatives for fractional exponents. It's because when you take the derivative of a fractional exponent, you take 1 away from the exponent, right? When you take 1 away from an exponent that is less than 1, you create a negative number, which means when you write it, it drops down to the denominator now. As soon as you have a variable in the denominator, what number can you not divide by? 0. So this function, where's the function? So this actual function has an undefined derivative at x equals 0, because when I do the derivative, this is what I get, and I can't put 0 in there. That make sense? Okay. Let's do another one. So what if you have so there's your function, 1 over x squared. You want to write it as x to a power, because then it fits our power rule. So we're going to rewrite it as x to the negative 2. And now we're going to do the derivative. So what do I do?
Drop the exponent minus 1.
Drop the exponent and then take away 1. If I take away 1 from negative 2, what do I get? Negative 3. Do not write 1. So you can either leave it like that, or you can leave it as negative 2 over x cubed. They're the same thing. Okay? Just be careful that you remember it's 3. Don't write 1 or negative 1 or something. All right? That's a mistake that people always make. We okay? All right. Let's just keep going through examples. Okay, D. Y is equal to x. What's y prime?
0. 1.
You did not say that with a lot of confidence.
1.
1?
Yes. 1.
Do we think it's 1?
Yeah.
So you can either think of the line, which is 1, and if you actually do the math, you drop the 1 down, because that has an exponent of 1, right? If I take 1 away from it, what do I get? 0. What's anything to the 0 power? 1. So you're just left with 1. Right? And that makes sense, because if you think of the graph, y is equal to x, that is horrendous, y is equal to x. That's still not great, but that works. The slope of that line is the number that's in front, 1. Okay? All right, let's do, you know what, that's, okay. I'm going to add a little wrinkle, or not a wrinkle, but we'll call it another rule. We'll call it the constant multiple rule. So number 3. Constant multiple Okay. The derivative is a limit, correct? Everybody's just silent. Yes, right? Because this is what we had from right there. Okay. If I have a constant here, what are you allowed to do using the limit properties with constants? You can pull them out, right? So if the derivative is a limit, and in limits I'm allowed to pull constants out, what am I allowed to do in derivatives?
Pull a constant out.
So if I have a constant c inside my function, you can pull the constant outside. So it becomes c times the derivative of f of x. Okay? So this allows us to do these types of problems. If I have y is equal to, I don't know, 3x squared. Basically, if I say, well, I can rewrite this. If I say, okay, do the derivative of this function. Okay. What can I do with the 3? You just pull it out. And then do the derivative of x squared. What's the derivative of x squared? 2x, right? Because you drop the exponent, take away 1. So I get 3 times the derivative of 2x, which is just 6x. Or we can
do that in one step.
yeah. Or nobody really writes it this way. What people would do is they would just go from here, and they would just go y prime is equal to 3 times 2x. Okay? But the reason you're allowed to do this is because you're actually pulling the constant outside of the function. Because it is a limit, so we can apply limit properties to it. Okay? So nobody writes it this way. They would just do, oh, y prime is equal to 3 times 2x. You would probably just write it in your head and just do that in one step. And just say it's 6x. Okay? But that's why you can do that. Okay. Because when you do the derivative, this says find the derivative. That's what that says. That is the derivative. You've done that operation. It's like if I wrote this 2 times 3, I just go that's 6. The operation goes away now, right? Because you've done it.
So it's just a really annoying way of saying that.
Do the derivative.
Yeah.
I wouldn't say it's annoying.
It is. It looks like you got a bunch of variables in there.
Yeah, it makes sense when you start to learn more about this. I know. So right now it's annoying. Okay. Just for you, Anthony. So why did I put a T there? Why did I put DT, I guess?
Respect to t.
Yes. So the bottom here, this thing, changes depending on what the variables are in your function. Okay? The derivative of this function with respect to t. The reason you write this with respect to t is because if you go on in calculus, you can have, and you've seen them, multiple variables in an expression, right? So sometimes you do what are called partial derivatives, where this is like second year calc now, where you just do it with respect to one of the variables. Only one of the variables is changing as opposed to all of them. So that's why we write it this way. Okay, but that's like a year and a half for you guys down the road. All right, what do I do? Do I care about the 4/5?
Just pull it out.
Yeah, I mean, we can just write it down. Now, What's the derivative of t squared? 2t. So what's my answer?
8/5t.
Yeah. Right? Is that correct? Or you could write 8t/5 or whatever. I don't care. But that's it.
8/5t.
Yeah.
Brutal.
Brutal. All right. Here we go. I'm going to give you one to play with. That is not 2 to the power of 3. That is 2 times the cube root of x squared. Go. So what do you have to do first? You got to do something first.
I'm taking half.
You can take the half out. There's one other thing you got to do too.
Like the fraction.
Go. Ready? -1/3 x to the 5/3, or x to the cube root of x to the power of 5.
I got everything right except the exponent was 5.
All right. So everybody pulled the 1/2 out, right? Or just wrote it down.
Yeah.
You dropped the -2/3 down. Everybody get that? Well, first of all, you have to rewrite it as x to the power of -2/3. People do that.
Yeah.
Okay. -2/3 falls down. You take away 1. Now, if you're taking away 1 from -2/3, you're going -2/3 minus 1. But you need to have a common denominator, so it's like 3/3, right? So it's -5/3. That's how you get that. And then you can just drop it down if you want to make the exponent positive. We okay? Yeah? All right. I want to do one more. Then I'll give you a few practice, and then I want to do the trig ones. Okay, let's do D. Oh, good and black. All right, we're gonna do. If I say y is equal to x cubed 2x squared plus x over x. I haven't seen something like this before. So, I don't know. There's a lot of stuff going on there. What the heck? All right. So, you're going to learn a formula next week called the Quotient Rule, which deals with dividing functions. But you don't want to use that formula unless you absolutely have to. And in this case, you don't absolutely have to. All right? This is tattoo this into your brain because it will save you down the road. Okay? Or tattoo it on your forearm like my Spider-Man tattoo. All right? If you have a single denominator, it goes to all the numerators when you're adding or subtracting like this. So this is the same as this. Correct? Because if you have a common denominator, then you just add the numerators, which gives you that. So we're just doing it in reverse. Why is this a good thing? What I just did.
Now you can cancel all the x's.
Yeah, you now simplify it, right? Simplify everything before you do the derivative. All right, that is your goal here. So this becomes x squared. This becomes 2x. What does the end become? 1. So now this is what I'm deriving. Y is equal to x squared plus 2x plus 1. Which still, we haven't done anything like this, but what do you need to remember a derivative is? It's a limit. And if it's a limit, what can you do when you have stuff that is being added together? We don't have to factor them all, but you can do each one separately, right? Remember, I can do the limit of this, and then the limit of this, and then the limit of this. And because the derivative is a limit, I can now just do the derivative of this. What's the derivative of x squared? What's the derivative of this?
Just 2.
It's 2, right? This is like the one we did up here. This one. Right? It's just, well, it's the number that's in front, essentially. Oh my gosh, come on. Okay, so then I get 2x plus 2. What's the derivative of a constant?
0.
0. I guess I should erase the plus. There you go. That's it. Okay? So if it has a single denominator, divide it off, simplify it, and then if it's a polynomial, which this is, just do each one separately and plug them all, add them together. Is that okay?
Can you do anything if you factor that, or is that wrong?
You could write 2 times x plus 1, but that, depending on what you're doing later on, right? It might be useful to do that, and in some cases it would be. It will be, actually, when we get into curve sketching, but right now, you just leave it like that. Okay, here's your practice questions. You're not going to get them all done because I'm going to give you a whole bunch. But I want to start trig in 15 minutes. At 1:30, we're doing trig. So 3 to 17 odd, 43, 45, 55, and 57.